നമുക്കിപ്പോൾ എന്തൊക്കെ കിട്ടിയിട്ടുണ്ട്? മെട്രിക് സ്പേസ് y d dash കിട്ടിയിട്ടുണ്ട്. ആൻഡ് y d dashൽ d dash എന്താണ്? It is defined by the d dash of two elements, the distance of two elements in y is equal to the limit of d of nth element of these two sequence. This is d dash. Next we need to prove that E of x closure, we need to prove that there exists an isometric embedding E from where to where, x to y, and E of x closure equal to y is complete, and then we need to prove that the metric space that satisfies all these conditions is unique up to metric equivalence. That is, if there exists any other metric space Z D double dash and an isometric embedding F which satisfies all these conditions, then Z D double dash must be metrically equivalent to Y. These are the things that we need to prove. So first we need to define such a function. Now let x be an element in x. Then consider the sequence xn, which is the sequence in which all elements is the constant x. Then we know that this sequence converges to x, which means this is a converging sequence. Every converging sequence is a Cauchy sequence. Therefore, constant sequences are always Cauchy sequences. Cauchy sequences for any x in x. So there will be a class represented by this Cauchy sequence in what? In y. Now define E from x to y by E of x is equal to this class, and it is defined for all x in x. So this is a function from what? X to y. Next we need to prove this is a isometric embedding. E is a isometric embedding. To prove this, consider d dash of what? E of x, E of y for two elements x, y in x, and this is equal to d dash of what is E of x? The class represented by x. And what is E of y? The class represented by y. And by the definition of d dash of these two classes is equal to limit of d of the nth terms of the distance of nth terms of these two sequences. So these two are constant sequence, therefore their nth terms are x and y. And d of xy is a constant, so the limit of d of xy is d of xy itself. Hence we got d dash of E of x, E of y is equal to d of xy for all x and y in the metric space x, which implies that E is a isometric embedding. This is the proof for the function that we defined here is a isometric embedding. Next we need to prove what? Next we need to prove that E of x closure is equal to y. For a set A closure is equal to y. If A closure equal to y, then A will be dense in x. We need to prove here E of x is dense in y. which means E of x closer equal to y. If each element in x is a limit point of A, then A closure will be equal to x. So, to prove A closure equal to x, it is enough to prove that each element in x is a limit point of A. And we can prove each element x in x is a limit point of A by proving any open ball centered at x will contain a point in A. Then x will be a limit point of A and x is arbitrary. Therefore, every element is a limit point of A and hence A closure equal to x and hence A is dense in x. This is the step we are following to prove E of x closure is equal to y. Now consider an element sequence xn from y and this is an element of y if and only if the sequence xn is a Cauchy sequence in x. By the definition of Cauchy sequence, for each epsilon greater than 0, there exists a natural number positive integer n such that d of xn is less than epsilon by 2 for all n m greater than or equal to n. Here we considering less than epsilon by 2 corresponding to this n by. When we choose epsilon greater than 0, epsilon by 2 is also it is also greater than 0. Therefore, corresponding to epsilon by 2, there exists a natural number which satisfies this condition. But we are taking already first we are choosing epsilon. So that I am writing here epsilon greater than 0, there exists and insists that these conditions. Now this is possible. Now choose m equal to n. Then we can rewrite this as d of xn is less than epsilon by 2 for all n greater than or equal to n. If we take z is equal to xn, then the sequence z, constant sequence z will be a Cauchy sequence in x. Therefore, the class represented by z will be in E of x. Why? By the definition of isometric embedding E, we have E of z is equal to this class. That's why this class belongs to E of x. Now z is equal to xn. Then we can rewrite these things as for any epsilon greater than 0, there exists an n such that d of xn z is less than epsilon by 2 for all n greater than or equal to n. Now from this, consider the d dash of the two classes represented by xn and the class represented by z. By the definition of d dash, this is equal to the limit of d of xn and the nth term of this sequence is z, because this is a constant sequence. And we know that d of xn z is less than epsilon by 2. Therefore, their limit is also less than epsilon by 2, less than or equal to epsilon by 2. And epsilon by 2 is strictly less than epsilon. Therefore, we can say that d dash of for any epsilon greater than 0, there exists an element z in E of x such that d dash of xn z is less than epsilon, which implies any open board centered at Xn contains an element in E of X. So every element and this is an arbitrary point that we choose from Y. Therefore, from this point is a limit point of E of X, and this is an arbitrary point from V. Therefore, we can say that each element in Y is a limit point of E of X. Therefore, E of X closure is equal to Y.